My name is Stephen Donnelly. I work at a company called Endace. We're based in New Zealand, and we do packet capture hardware and appliances. I'm not going to talk about our products here as much as possible. We are sponsors, so if you'd like to talk to us a bit more, we'll be at the vendors dinner, the vendors area later. And I'm around for the whole conference, so you can talk to me directly as well. All right, so what I'm going to talk about today is metadata, essentially, right? So what I'm interested in is what is the context of when you're doing packet capture? And this is something which I think is under the area of process today, right? So maybe you've got a notebook and you make notes, but we want to try and capture that a bit better. All right, so I think everyone here is either doing packet capture today, or you're working with trace files that have been captured by somebody else, or you're planning to do one of those two things. And I think we all have a pretty good idea of why that is, right? In fact, I think Jasper was wearing the shirt earlier. We like packet capture because it's considered ground truth, right? If you've got a packet capture and you're trying to determine what the source of the problem is, then you can rely on that to, as evidence, right? A packet capture is really the most reliable way that we have of indicating where a problem is actually coming from. But I had an interesting comment from one of our customers who said, packets don't lie unless you don't know where they came from. Right, so packet traces are fantastic evidence, they're great ground truth, but there can be problems with them. If you've got a packet trace, particularly if it was captured by someone else and given to you as an analyst and you're trying to work with it, there can be problems with it. If you don't know whether capture was performed in the network, that can have a big impact. Right, so if you're looking at a client-server problem, does it make a difference whether the capture was performed close to the client or close to the server? Yeah, it does, right? So if you're not seeing packets in one direction, is that a problem in one end of the network or the other? Packet traces can also be misleading if there was packet loss at the time of capture and you don't know about it. So you may not actually have all of the information that was there on the wire. Sometimes you can infer packet loss from application behavior, but sometimes it's more difficult to see. Another thing that happens is often when you're dealing with a packet trace that's been provided by someone else, whether it's a colleague or a customer or whatever, there may be some filtering that's gone on. So you might be looking at that trace and saying, well, how come there's no DHCP or how come there's no DNS? Well, the previous user may have already filtered that out, so you can't see it. And if you don't know what the filter was that they used, you don't know what you're missing, so it makes it a lot harder to interpret. And then finally, packet traces always have timestamps. But if you don't know what the quality of those timestamps is, then you don't know whether you can trust any of the timing-related measurements, right? So that's not just time of day, so what was the date and what was the time that the capture was performed, but what was the quality of the clock that was used for that. So if you're trying to measure your round-trip times on the network, server response times and things, you need to know whether or not your timestamping system is synchronized correctly, whether it's actually working properly. So these are all contextual metadata items that you really want to know about in order to be able to reliably interpret a trace file. So what I'm going to talk about is basically, why do we need metadata? What's it for? What kinds of metadata might be useful? What sort of metadata is available today? And then we'll have a look at a couple of different ways in Wireshark that you can look at metadata. There's a couple of different formats to look at, PKPG and ERF, and we'll look at how they differ and what difference that makes. Why those two particular formats, you might be asking? If you look at Wireshark, it can capture something like 30 or 40 different file formats that it can open and understand. The reason I picked these two, PKPNG is the default capture format in Wireshark, and ERF is the Indace extensible record format. These are the two formats that support the greatest variety of metadata in Wireshark that I'm aware of. So if anyone else has got examples of capture file formats that have good metadata recording in them, feel free to let me know. We can talk about those too. So why is metadata important? Lots of different reasons. When you're doing a capture on your laptop, it's ad hoc, it's for a short period of time. You're the one doing the capture, so you kind of know what the context is. You know where you were, you know which port you plugged it into. You can make notes about all of those things. If, on the other hand, you have a large corporate or enterprise type network, you've got multiple capture systems throughout your network, you may be doing captures at multiple points within the network simultaneously and recording those into a single file. So scalability is important. If you're capturing from multiple interfaces, you need to know which packets came from which interfaces. Data mining, obviously what you want is a data lake, not a data swamp. So the quality of the metadata about what you're putting into it is very important, and again, helps you to actually interpret that later on. Capture quality is important. Did you lose any packets? Was there any filtering that was going on? Clock synchronization performance is becoming more important, so particularly in the financial industries. So we're seeing in Europe with MiFID II, the regulators are now saying if you're a trading organisation, you have to record all of the market feeds that you get. You have to timestamp all of your trades that you're doing, and you have to be able to prove that the timestamps are accurate. So they're trying to get a very high-level view of the markets. It's also useful in general for event correlation. So often when you're looking at packet traces, you're looking at the timestamps, you're comparing this to some other system. So you might be looking at application logs or security event logs, IDSs, and having all the clocks in the system synchronized means you can do that correlation much more easily. Which is the security network event annotation as well. So if you're trying to match up security events across different types of systems, compare that with packet traces, it's much easier if you know that those things are connected, and you have some way of tagging alerts and things back to packets or flows that are related. Okay, so that's kind of where we're up to. That's kind of why I think metadata is quite important. So what is metadata? I think we all have a pretty good understanding of what metadata is. Here's a photo that I took in Auckland, for example, and within that JPEG file there are some EXIF tags. You can use Wireshark to look at the tags. The dissector for them is not very good, so I'm just using the Windows picture viewer here. But the point is that it gives you a bunch of interesting information about the picture. So things like the size of the picture. It's not working. Oh, there we go. The size of the picture, the technical details of how it was recorded, what the shutter rate was, the type of device that it was, and the location. So the date and time is kind of useful because the file time will change, right? If I email this photo to somebody else, then the date of that picture on their machine is going to be different. But the timestamp that's recorded inside the image file is not going to change, so that's more reliable. The map here is provided by Bing, so it's not very useful, but it is wet, obviously. But again, having that location information recorded in the picture makes it much easier to understand where the picture came from. You can search on it, all those kinds of things. So that's fine for photographs, but what about network packet captures and packet traces? What kinds of things might we be interested in trying to collect? So I would sort of go back to the classic journalism, who, what, when, where, why, and how kind of questions. The what, in terms of what happened on the network, well, obviously we've got the packet contents if we're capturing packets, so that's straightforward. There may also be flags, like error flags and things, capture filters, search terms, the timestamps on the individual packets, but also what was the clock synchronization system, so what was the reference, where was the data collected, so what was the interface that it was captured on, what card was it, which system was it within the network, what was the name of the site or the link, where was the location of the machine that was doing the capture. So we've seen people using GeoIP to identify where endpoints are based on IP addresses and alias numbers, but what about the actual capture system itself? Often we don't know that. There's also a question of why did we capture that traffic? That might be related to a trouble ticket number or a SEAM event, an IDS alert or something like that. There may also be user comments, so there may be a trace comment that describes some of that. If it's a control system, what's the classification of the information, who authorized the capture, who actually performed the capture, and then how was the capture actually performed? So what was the hardware that was used, the OS, the application, what were the different link states if you're capturing on multiple interfaces? If it's a radio interface, then obviously there's a lot of metadata related to signal strength and channels and things, and even link speed for wired networks. So when you think about it, if I have a trace file and I see a spike of traffic there to 800 megabits, is that a problem or not? Well, it kind of depends on whether it's a 1 gig link or a 10 gig link or a 100 gig link, right? So the context of what was the link that I was actually capturing on is quite important as well. Okay, so I think beyond that there's sort of different types of metadata as well. You can divide it into a few different groups. There's static metadata, which is the kind of thing which doesn't change throughout the lifetime of a packet capture. So things like the host system details, right? The model of the machine that you're doing the packet capture on doesn't change while you're doing the packet capture usually. What were the capture interfaces? What was the version of the software? All that kind of stuff is kind of fixed. But there's also dynamic context. So if you're looking at clock synchronization, you could just say once at the beginning of the file, oh yeah, we were using NTP. But rather than doing that, you realize that NTP varies over time. So you want to capture the behavior of that throughout the trace, particularly if it's a long one. Some traces are quite short, but trace might be an hour long. NTP could do a reset in the middle of it. Other things that vary while a capture is in progress, link state and speed. So you could actually have somebody unplug a cable, plug it back in, auto negotiates at a different rate. Radio networks are changing all the time. Optical power for fiber networks. And then finally, another form of metadata we don't always think about is metadata that's added after the capture time. So static information and the dynamic information can be collected while you're doing the capture, but we may also be adding information to the trace file later on. We've seen some examples of that today. So things like user comments, so commenting on a packet in Wireshark. Events or alerts, so you may have information coming in from separate IDS systems or SIMs and SEAMs. Flow records, DPI information, we just heard Luca talking about using NDPI, annotating information into a packet trace, either during capture or afterwards. Or you could even have buzzwords today, right? AI and machine learning, so you can have systems which are doing some behavioral analysis, for example, and then adding information later. So how would we go about capturing this information and storing it somewhere? There's kind of two options for it. One of them is to collect all that information and store it somewhere else, right? So I can have my notebook, I can write down details about where was I at the time, which machine was I using, all that kind of stuff. Or I could put it in a separate file. I could have a notepad file open and I could write stuff down. The problem with that is if I then email that trace file to somebody else, they don't have my notebook. So you lose the connection of the metadata to the actual trace file. So I think putting all of the metadata that we can, putting it inside the trace file means you don't lose that association. Okay, so when we kind of think about how we've been doing packet capture for decades now, the most common format is still PCAP. That's the original TCP dump format that goes back to the 80s, I think, or at least early 90s. And when you think about what's in a PCAP file, there's actually very little information there. It's a file format, it has a file header, there's a magic number at the beginning, which you heard a little bit about earlier, and it can tell you whether the format is microsecond or nanosecond. There's a PCAP version, there's a time zone information, there's a timestamp accuracy field in the PCAP header, but I don't think anybody uses it. I don't think even the PCAP implements anything to do with it. There's a capture length, there's a link type. Now, of course, PCAP only supports one capture interface, and it only supports one link type per file. And then you get a sequence of packets. There's a packet header with a timestamp, the captured length, how long the packet was before it was truncated, and then the contents of the packet. And if you open a PCAP file in Wireshark, you'll see what that looks like. I'll zoom in on a couple of details. First of all, if you look in the frame dissector, that's basically all the information that Wireshark has either read from the file format about the frame or that it's calculated itself. So things that Wireshark has calculated are in square brackets, and then things which are not in square brackets usually have come from the file. And you notice that there's nothing in here about which interface it was on, because PCAP only captures from a single interface. So there's no way to distinguish that. Okay, and if you go to the statistics menu, I think it is, and go to the trace capture properties, it will give you some summary information about the trace file. And you notice there's a lot of unknowns here. So in the capture section, it talks about hardware, the OS application, and PCAP are unknown because none of that information is recorded in the trace file. The interface is also listed as unknown. It doesn't know whether there was any packet drop. It doesn't know whether it was filtered or not. It does know that it was Ethernet. So that's one of the few things that's actually in the PCAP file here. The information down below that, the statistics are all calculated by Wireshark. So that's not information that's in the trace file. It's all collected separately. There is the capture file comments box, but the PCAP format doesn't support that. So you can't add them and you can't read them out of a file. So if we kind of go back to our list of what kind of metadata might be useful and look at sort of coverage, PCAP's pretty terrible. So hopefully we're not using PCAP anymore. So obviously this is a problem, and people have been thinking about this for quite a long time. And the solution, or one of the proposed solutions to this is PCAP-NG. So this is not a new solution. It's been around for quite a long time. There are IETF drafts back to at least 2004 discussing the format, proposing it. I don't think that any of the drafts have been accepted yet, and there was another go back in 2014. How PCAP-NG works is that it's another file format, so it is specifically a format for files in storage, like on disk. It has a lot more metadata than PCAP does. There's about 30 different tags that are available. It's a tag length value type coding. It supports multiple packet interfaces, and it's extendable. So although there's 30 different things defined today, there's a wide namespace. Developers can go in and can add more features to it going forwards. It's been supported in Wireshark since at least 1.2, as far as I can tell, 2009. That was read capability for it, so I can read those files. You can also read PKPNG files into the PCAP since the PCAP 1.1, and that means that any program which uses the PCAP to read PCAP files can also read PKPNG files, but the way that it reads it is not very rich, so you lose a lot of metadata when you do that. And finally, it is the default save format in Wireshark since 1.8, which is back in 2012. So it's well supported. If you're interested in finding out more about it, the specification for the format is actually on GitHub. So you can go there, and there's a group of people who are maintaining that and discussing changes to it. So how it works, PKPNG's got a number of different blocks which have been defined, so this is all in the standard. The way that it works is that I've listed the different blocks here. The things which are in bold are mandatory within the block, and the italic ones are options within the block, so they don't have to be present. So there's a section header block which has the version in it, and it can store that hardware OS application information that we saw in Wireshark. There's an interface description block which has information about each of the capture interfaces. They must contain the capture length and the link type. But you can also store the name of the interface, what the address of the interface was, like the MAC address or the IP address, what speed the link was, what the timestamp resolution was, if there was a capture filter there, and what the checksum length was. And that's kind of useful just because some capture systems capture packets with the checksum present, and some of them strip it off. So that's what that's for. And then there is the packets themselves are stored in what's called an EPB, Enhanced Packet Block. There were a couple of other types that have basically been deprecated, so this is the one that we use. And you get, every packet has an interface ID in it, timestamp, the length of the packet, and the packet contents, same as you get in PCAP. You can optionally have flags, like error flags. There's a hash, which is actually basically a hash over the packet contents. So it's not to do with flows, it's to do with being a signature for that individual packet, so you can recognize it different places in the network. There's also support for in-band drop information about where packet loss occurs in the file. PKPNG also defines a name resolution block, so you can store within the trace file mappings of addresses to names. Finally, there's an interface statistics block, which has a start and an end time, plus counts for received, dropped, filtered packets, and things like that. The way that the blocks are implemented is sets of tag length value options. There's plenty of address space in there, there's 16 bits. And there's a special tag type, which is a comment tag, which is just a string, and that's allowed in all of the blocks. So you can have comment can be inside a statistics block or a packet block or whatever. There's also a number of experimental blocks defined in PKPNG, but they are very only loosely defined. So there's no working definition for them. They're really just proposals. So what does it look like? So specifically, this is kind of what a PKPNG file looks like as supported by Wireshark. So the file is defined to start with a section header block. Then you can think of this as being a file header. Wireshark, as far as I know, only supports a single section within a PCAP file, PKPNG file, even though the format says that you can have multiple ones. The section header is then followed by a lot more interface description blocks. So in this case, I've got 3. You've got a number of EPBs, the actual individual packets. And each one of those EPBs refers back to one of the interface description blocks. Then at the end of the file, this is where Wireshark puts them. So if you turn on name resolution, then Wireshark will create name resolution blocks at the end of the trace file, so after all the packets. The standard doesn't say that, you can put them anywhere. This is what Wireshark does. And then you get, what Wireshark will do is it will put these interface statistics blocks at the end of the trace file, at the very end. And there will be one interface statistics block for each interface description block. So if you're capturing on 3 interfaces, you get 3 IDBs, 3 ISBs at the end. And the reason for that is that the ISBs can only refer to a single interface at a time. Now, I noticed something interesting when I was reading through the user manual on Wireshark.org, which is the user manual says that resolved names in a capture file, so if you're in Wireshark and you turn on resolved names, the user manual says that they're not stored in the capture file. If you use saving in PKPNG, they are. So there's a discrepancy there. Except for the fact that when I was working on this presentation, I tried it out and found that it doesn't work. So there's actually a bug in Wireshark 2.2 where the resolved names are actually not written into the PKPNG file, and nobody noticed. What should happen is if you open a trace file which has had resolved names in it, then it should populate them immediately without having to look them up again. And that bug has now been fixed, by the way, and backported to 2.2, so the next stable version will have that fixed in it. Alright, so if we have a look at a PKPNG file in Wireshark, here's the packet list. The first thing you might notice is where is the section header block and where is the IDBs and things. They don't show up. Okay, Wireshark doesn't dissect PKPNG as if it was a wire protocol. Instead, what happens is when it opens the file, it reads through all that information, stores it internally, and then uses it to populate different parts of the user interface, but they don't show up directly in the packet list. So if you go down to the frame dissector and have a bit of a look, the first thing we can see is different is that there is now an interface ID listed here. So it's interface ID 1, that's a number assigned by Wireshark, it's just the order the interfaces turned up in, and the name is the capture interface. So this is a file that was captured in Windows, which has advantages and disadvantages. The name of the interface is not very human-friendly, but it does have a GUID in it. So in theory, if you've got multiple PKPNG files, you could start collecting these interface names, and you would know when 2 captures have been performed by the same machine. In Linux, what happens is you get the name of the interface. So on most Linux distributions, you just get ETH0 for the name of the interface, which is not very helpful. It's not a GUID, but it's a little bit more, perhaps, user-friendly. Okay. And then if you look at the capture summary, what we'll find is that now a lot more of the fields are filled in. So previously, the whole capture section was empty in the middle there. This bit up here. Because it was capturing Windows, the Windows Wireshark currently doesn't capture any information about the capture hardware, so it's still listed as unknown. The OS is recorded, and the application and version was captured as well. So this is Wireshark 227. If you're capturing Linux, the capture hardware is listed, and what it will give you is, I think, the CPU model string. Strangely enough, so what you get is it'll say something like, i7 740 V2 3 GHz or something like that, which I guess gives you some idea of what kind of machine did the capture, but it's not really very helpful in a lot of ways. There's also a few more fields that are filled in the interface section. So we've got the names of all of the interfaces that occur within the trace file. So this particular file's got 2 interfaces. It will tell us whether any of those interfaces recorded packet drops while the capture was running. If there was a filter that was set on the interface, then it will record what the filter was, as well as the link type. And the maximum packet capture size limit. Again, it's captured in Windows and it's defaulting to 262. So this one is just scrolling down a little bit. Down at the bottom you've got the file comment. So this is this add name resolution is the comment that I put on this trace file, and that's stored in the section header block. So that's where PCAP puts the trace file comment. Wireshark only supports one comment on a trace file, so you need to be aware that if you edit the trace comment and then save it, then the old one is gone. Right, so just overwrites it. If there are per packet comments recorded in the trace file, they'll also show up here as well, just for convenience. So here's an example of packet comment. When you are in Wireshark and you right-click on the frame and you add a packet comment, it's just storing it in memory, so it doesn't modify anything until it actually saves the trace file again. When you save the trace file, it rewrites the whole file back out to disk, and it adds the comment as a comment option inside the specific packet block for that packet. Okay. So, what's our coverage look like? It's looking a lot better, I think. So with a few caveats. So we do have a couple of minutes. So the hash there is the packet payload hash, it's not a flow hash. The capture filter, which is listed here, is Wireshark's capture filter, which is a BPF format string. It's not a display filter. So what you might think of as a search term or a display term doesn't show up. So if you're in Wireshark and you apply a display filter and then you save the exported packets, it doesn't record what the display filter was at the time that you saved it. It will maintain the capture filters, but it doesn't update them. It doesn't tell you what the display filter is. So something to keep in mind, if you do that, you may want to just copy and paste your display filter into the trace comment field. Otherwise you'll lose that information. The timestamp resolution information, as far as I can tell, isn't displayed in the UI anywhere in Wireshark, but I think it is used to set the timestamp column width. If you set it to auto, there's an auto setting in there. If your PCAP file supports that timestamp resolution field, then it will adjust the width of the seconds from microseconds to nanoseconds and so on. The hardware model, as I said, isn't recorded in Windows, but it is in Linux. It may not be very helpful. And comments are kind of a get-out-of-jail-free card. So for all the things that are not recorded in here, like the clock source, clock sent state, what was the capture site, what was the name of the machine that I did the capture on, you can use the trace comment to fill that stuff in. But the disadvantage is it's manual. Right? So it's a process thing. It's up to the operator who's performing the capture to go ahead and do that, and that's most likely not going to happen. Right? So it's about discipline, and you would have to actually have a process to say, okay, when you capture a trace file, put in your username, put in the date and time, put in the site that you're at, all of those things. So an alternative is the ERF format. This is the index format. It's produced by more modern cards and the appliances. The difference compared to PCAP and PCAP-NG is those are both file formats. This is really more of a streaming format. So it's not specifically about packets on disk, but more packets as they're being captured, and a file is simply a sequence of packet records on disk. There's been no support in Wireshark since before it was Wireshark, so going back to Ethereal in 2003. It is fully supported in stable Wireshark. We're actively developing it. You can do live capture from DAG cards just using the PCAP if you want to in Wireshark. And there is a complete ERF dissector, so you get all of the area fields are dissected as visible values, and you get expert info and things like that. And what we've done more recently is in 2016 we've added support for storing metadata in this ERF format. So look at how that's implemented. basically what we've added is a new record type. So in Earth, essentially you get a series of records, each one of which encapsulates one packet. With provenance records, you get metadata. So they can be periodic, so we can drop metadata in, say, on a second boundary or per hour or whatever. And you can also insert provenance records to describe particular events that happen, like a link state change or something like that. There's information there about interfaces, flows, packet annotations. There is a scalability feature for addressing interfaces. So we saw that in PKG it recorded the interface name, which in Windows is a GUID, but in Linux it's just ETH0. So here we have a naming scheme which includes the capture host, the capture module within that system and the interface. There's the time that the metadata was generated, which may not be the same time that the packet trace was recorded if it was added later. And we've got 160 plus tags defined. The format supports comments on flows as well as on packets, but Wireshark doesn't support that yet. And I'll get into comments a little more in a few slides. All of the 160 plus tags that we've defined in the standard so far are dissected by Wireshark. So Wireshark understands all of them, dissects all of them, displays them. Most of them are displays fairly nicely. Not all of them are generated by the traffic sources at this point. So some of them are slightly ahead of the implementation side. And if you're capturing files in Wireshark, they aren't necessarily going to use all of those tags. So what does it look like? So a provenance record has multiple sections within it. And the sections, broadly speaking, are information to do with the capture itself, information to do with the capture host, information about the capture cards or modules, the interfaces on the card, and multiple streams. So a lot of capture cards today support multiple queues or streams of information. The sections are kind of similar to the PKG block types. The capture section has got a name and description, what the application was that was used to generate it, who the user was, what time zone the capture was done in. For the host, we've got things like the capture host name, the OS version, CPU, RAM, the organization, the location of the system, the module section, or the capture card, if you like, the hardware. You can store the model, the serial number, the firmware versions, the configuration mode of it, what the clock sync was. If you're using PTP, you can record information about what PTP Grandmaster was in use at the time and what the error estimates are. The interfaces, that's the physical, physical ports. We're recording the SFP vendor and model, the receive optical power, which is dynamic. And then for the stream section, it's able to record how much memory is allocated for the buffers, and also whether any packet drops have occurred within that stream. So what it looks like is basically a series of packet records, which are the orange ones, and then periodically we insert provenance records as needed. So they can be purely on a time basis, or they can be documenting specific events. So when you open one of these files in Wireshark, it looks fairly normal. One thing you'll see is that record 5 there is the protocols listed as Earth, and the information says that there's provenance metadata in that record. And you notice that the timestamp is all zeros at the end, so that's a periodic metadata record that was inserted on a second boundary. And if we look at the frame that's currently highlighted is frame 1, so it's just a regular Ethernet packet. And when we look into it, we can see the interface name. So again, there's interface ID 0. It's been assigned by Wireshark. and then the port information. So there's the name of the interface, which on this particular interface was just called port A. It's a default name. And then you've got the host ID, which is a 48-bit number, the capture module, and the interface ID. So that information all comes from the provenance record that this packet is linked to. And if you scroll down a little bit, the packet record has an extension header on it. The extension header has a host ID in it, so that tells us for this particular Ethernet packet which capture host was it and which source ID within that capture source was it. And that is a link within Wireshark that if you click on it will take you to the provenance record that describes that capture interface. And looking at the capture file summary, dialog, again we've got the little bit more information than we had before. So this particular ERF file was captured on a Linux machine. It's running CentOS. Here's the host name for the machine, the host description rather, which is the field that's used as a preference. If the description is not available, it'll display the host name there instead. And also we've got this string, which is basically what PCAP-NG will tell you if you're on a capturing from a Linux system. So basically gives you that CPU info string. And then the application that generated the metadata was called DagMeta version 551. Scrolling down a little bit, you can see the interface ID, host name here. So you've got again the friendly name followed by the hierarchical name, which is the host ID, the source, and the interface. The packet drop count is listed as unknown, and the reason there is that IRF tracks packet drop on a per stream base, not on a per interface basis. So the drop information is there, but we're not tracking it on a per interface basis. There wasn't a capture filter assigned, and you can see that the snap size was 9K. So if we have a look at one of the provenance records, the difference here is that they are dissected as if they were a wire protocol. So that means they do show up in the packet list, and you can click on them and you can see all of the contents as if it was a regular packet. So Wireshark has a concept of a non-packet record, and these records are flagged as non-packet records, but they still show up in the packet list. In the future, there may be some visible indication in the packet list, some sort of marker to show that it was a non-packet record. At the moment, it's not immediately obvious. If you are confused by them, you don't want to see them, you can very easily filter them out just by using a display filter to drop the IRF-type meta records and just hide them. So if we have a look in here, we can see the host ID information again, so that's what this record is describing, the time that the metadata record was inserted into the trace file, and then the set of different sections. And right down the bottom there, you can see, as you know in Wireshark, when you hover your mouse over any dissectable field, you get the name at the bottom left. So you can see that all the fields which are in here are also broken out as dissection fields, so IRF, meta, section module, clock port protocol, for example, as one of them. It just happened to be randomly selected as I was scrolling around. And that means that any of the metadata can also be, any metadata that you've recorded, you can also use as display filters, right? So I can say, show me all of the metadata records where the clock was not synchronized or where the interface was down. And that will then give you a time range of where you need to look to understand what was happening there. Was it a question?
Is there an easy way to tell what's the actual interface on the host? Or does it say like EH0 for example, or it just says that string and you need to map it somehow?
Right, so the question was, I think, is there a way to set what the interface is called, or?
It has a name in there, but it's not necessarily a name on the operating system. How does it show in the captured area? How do you map this to the operating system name?
Right. So what PCAP-NG does, as we said, is a little bit different than depending on whether it's in Linux or Windows. What happens here is the user configures what metadata they want to store. So if you want to call, if you want to name an interface after the name of the link that it's attached to, so if you've got a feed that goes to Verizon, you can call it Verizon 3 or something like that. The metadata also records the IP address of the interface that was captured, if it has one, and the MAC address. We just had to pick a field to use in the actual interface name list, if you like. So that's what that is. You can also there's also a description field, so you can actually write a little essay about what that was, if you wanted to. There's a config file that sets out which tags you want to include, so you can choose whether or not you want to put the host name of the capturing system in, right? That could be a problem, so you can choose whether you want to do that. So the point is that the prominent records aren't dissected, they're visible in the packet list. You can get rid of them if you don't want to see them. Blowing up the different sections, give you an idea of what kind of information is there. So the capture section, it's kind of that very high level information. You can put in strings to describe things. One of the differences is that because this is not just a generic comment field, which is going to be named the same everywhere, they are actually broken out as separate items. The host section has got far more information about the capture system than what we saw in PKPG. So rather than just getting a string that tells us what the CPU is, we get a whole bunch of stuff. We get the system host name, you can put in a description, the organization, where we can describe where it is. There's also records for GPS lat long, if you want to go to that level of detail. It will automatically pull out the vendor and the model information from DMI tables, if they're available. It will give information about the amount of RAM in the system, the CPU models, cores, all that kind of stuff. It's all filled in automatically if you enable it, so it's not something you have to go into manually. About the capture module, right, so the capture hardware directly, there's even more information. There's a number of different sections here, so you've kind of got what the model was, the firmware that was running at the time, the serial number, all that kind of stuff. And then there's a bunch of information about the clock. So the synchronization threshold, the offset to UTC. If you're using PDP, then it will tell you what the grandmaster is that you're using. PDP will give you some useful numbers like what the offset from the master is. So it currently believes, PDP thinks that the capture clock is 18 nanoseconds off from what the grandmaster is saying. And you get all of that kind of information there. It tells you that it's coming from GPS upstream, that PDP is in slave mode, all of that kind of stuff is recorded periodically. We look at individual capture interfaces. This trace is a little bit unusual because it was actually captured on a 40 gig port, so it's a 40 gig interface, which is made up of 4 SFP modules gammed together, if you like, to form one 40 gig interface. So we get information about all 4 of the SFP modules, the vendor and model numbers, as well as the receive and transmit optical power, and the link rate, the link state, and so on. Again, that's just updated each second. And we've got the information about the stream, which is really just the size of the stream buffer, so it's allocated 64 megabytes here, and the drop counts. So we can see that there's no packet drop at this point in the trace file. Because this is added periodically, you can watch this over time to understand if there was packet loss in the file, at what point did it occur, which you may not see otherwise. So I think, coverage-wise, we've defined tags for everything that we could think of in terms of useful metadata to be stored. One point to make here is that all of these tags that have been defined are supported by Wireshark. If there is a new tag defined in the future, Wireshark will display the tag number and it will give you a hex dump of what the contents of it is if it doesn't understand it, but it won't break. And although all of these things are recorded by, supported by the format, it doesn't necessarily mean that they're going to be present in any particular trace file, in a specific file. Okay. So one thing that's worth talking a little bit more about is how comments work. PKPNG has got comment string options, and you can put a comment into any block type. And the way that it implements that is it just adds a new TLB option to that block, and then when you save the file, it rewrites the entire file out. It doesn't matter whether it's a few kilobytes or several gigabytes, it'll just write the whole file back out. ERF does something slightly different. Because the extension headers in ERF are not variable length, there's no length option, you can't just put a string in. So what we do instead is, if you want to add a comment, we add a new provenance record. And then one of the advantages of that is that we can record more information. So rather than just recording the string, we can record things like at what time, what was the date and time that the comment was added, who added it, what was the host ID of the machine that was used to add the comment, and so on. And in future you can add more things to that as well. So if you have automatically generated information that can be put in too. The record is dissected in the packet list. There's a link in the provenance record that links it to the specific frame that you're commenting on. Wireshark parses all of that and will put the comment on the correct packet exactly the way that it does for PKPNG. As a note, the ERF comment support is not merged yet, so it's not in a stable release. It's in a pull request, so we're just waiting on that. The generation time of the metadata is when you save the file. So when you go ahead and save that comment, it'll write the generation time into the record. And although ERF has the concept of a flow comment, so a comment that applies to multiple records, Wireshark doesn't really have a very good interface for that at the moment. So we're still thinking about how we would go ahead and do that. One way to do it might be to think of it as a conversation comment. So a comment that's attached to a conversation. As an example, this is kind of what would happen. So we've got a trace file, packets A, B, and C, frame 1, 2, and 3. If you want to add a comment onto frame 3, what we do is we insert a new provenance record in between the two. So the comment record becomes the new frame 3. The frame that was 3 now becomes 4. It's a metadata record. There's an anchor number in it, which is local to the commenting system, which links it to the original packet C, which has a new extension header on it, and we get these extra fields. So we get the time that was generated. You can see that this is actually much higher than the time that the packets were captured. The timestamp on the record is just copied from the file that we're commenting on. You get the username and of course the text string. The username actually does work in Wireshark today. So when you're in Wireshark, it can get the user ID of the person who's logged in at the time, and it will record that information as well as the commenting time. So you get slightly more than you would if you're just using PKPNG. So one suggestion would be if you are using PKPNG and you're adding a comment, you might want to think about adding the date and time and who it is who's making the comment, particularly if it's a file you can share with other people. So, as a summary, what are some of the differences between the two approaches? PKPNG is very much a file-based approach. It's a file-based mentality. So you get a file header which has the static metadata in it, but there's not very good support for dynamic metadata. There's options you can add to individual packet records. You can put in statistics blocks periodically, but the contents of those blocks is very tightly defined. Whereas in ERF you can put any tag and actually go in any section. So PKPNG I would say is best for sort of ad hoc packet captures where the environment is static throughout the capture. And you've got to keep in mind that you have to add a lot of that contextual information yourself. It's manual, it's not automatic. If is more of a streaming approach, you get a complete update of all the metadata every second, and that makes it easy to extract a time period. So if you have a rolling capture, you might have last 2 or 3 days worth of data recorded. At any point you can say, oh well, on Sunday at 1 o'clock in the morning something unusual happened. I can go back to that trace file, take out a section of the trace file just based purely on time and nothing else, and I know that the metadata associated that was current at the time of capture will be extracted with that. It's pretty lightweight. It only adds 1 packet per second per capture interface. It scales very well. We've got people with something like 2,000 capture nodes, and any single capture file could potentially contain packets from any of the interfaces on any of those systems. So having some way of dealing with large numbers of interfaces is quite important. And I would say that it's well suited for continuous capture, if you like. So rolling capture where the environment changes over time, and you want to know about things like the capture interface went down. So if you're in PKPNG, you'll see that there's no packets there, but you don't necessarily know why. Here you can annotate that event, and the link state gets recorded each second. So in some conclusion, trace metadata I think is really important. It provides the context that you need to interpret packet traces and gain information from them. Particularly important where you're sharing files with analysts or with other people. The provenance and the quality of the packet trace matters. So it's not just having the packets, but it's knowing that they were captured correctly, that the timestamps were correct and so on. And about maintaining a history. So another slight difference is when you edit a comment in Wireshark, if you save that in PKPNG format, it simply overwrites the existing comment. So if you want to add another comment to a packet, you have to append it, kind of add it on the end. And with ERF format, if you edit a comment, it adds a new provenance record. So you'll actually have multiple provenance records with the generation time and the user in the previous versions of the comment stored in the trace file, so you don't lose that stuff. There's different types of metadata. Automatic metadata is the best because users are not very good at manually recording all those details when they go to do a capture. It's already in Wireshark, so metadata support has been around for a while. If you're not, perhaps use PKPNG. If you're sending a file to someone else, ask whether they can use PKPNG rather than plain PCAP, because they'll get more information. There we go. So, any questions? I've got a question for you guys, just a quick poll. We saw 2 different approaches there. PKPNG, all of the information is hidden. So if there is a new field that's added to PKPNG and Wireshark doesn't understand it, it doesn't dissect it, so you can't see it. It's all hidden from the packet list, and Wireshark just picks out individual pieces of it. With the ERF, what we decided to do is to make it a dissectable protocol. So the dissector is available, it's open source, you can look at it. And all of the individual pieces of metadata are available as dissected fields. You can do display filters on them. You can create I/O graphs of optical power over time. You can do all of that stuff. So who thinks that the PKPNG got it right, and that the best thing to do is to kind of interpret the information but hide it? Any hands? No? Maybe? Not sure. How about with ERF, where we've actually explicitly dissected it and made the metadata kind of a lot more visible? Does that seem like a better approach? Yeah? Okay. Anyone's not sure? Hasn't put their hand up yet? Okay.
I think the problem is we are where we are with PKPNG, aren't we? So it's already being used in Wireshark, and it is extendable. So
it is, yeah. So one issue there is because it's extendable. If somebody gets enthusiastic and goes and adds a bunch of these fields to PCAP-NG, old versions of Wireshark won't display it anywhere. And because it's not dissected, it's completely invisible. And as I said, one of the things I discovered when I was developing the presentation is I was looking at the NRB blocks, and I turned on name resolution and I saved it, and I looked at the file, it didn't get any bigger, and I was trying to understand what was happening. So I had to get a hex editor out to open the file and then start parsing through the hex to try and find the blocks and find out what was in them. And it turned out that because of a bug in Wireshark, it was only saving names that the user had manually resolved. So if you right-click on a thing and say resolve this as Bob, it'll save that. But anything that was resolved through the async resolvers was getting discarded. But that was completely invisible in Wireshark, whereas in ERF, the name resolution blocks, when they get added, are all visible at the end of the file, so you can see where they are. And we're kind of thinking what we'll probably do is, well, an extension would be rather than putting all the name resolution blocks at the end, we'll sort of dump them every second. So if you have a long trace file, rather than having to read through the end to get the name resolution, it'll be within a second of where we first saw that address. Any other questions or comments?
So today you're generating the ERF using, you need a DAG card, right?
Mm-hmm.
So that's the only way you're going to see the host information. Where do you guys see trying to get this into a Wireshark build, get more of ERF support? So save this as ERF and get that information. What do you guys see NJ's doing?
It's a good question. So you can, if you're in Wireshark and you're capturing, you can choose to save as ERF. And what will happen then is Wireshark will attempt to generate metadata based on the information that it has. So if you do save in ERF format, you should get that, that Windows GUID interface name will get written in. But part of the problem essentially is that Wireshark doesn't collect a lot of information at the moment. And because some of that is going to be dependent on the adapter type, so some of it you might be able to get through something like ETH-tool, you might be able to collect some of that stuff, but a lot of it just isn't available. We also support some conversion between formats, so as much as possible ERF is a superset of PCAP-NG. So if you start with a PCAP-NG file, you can convert it into ERF and hopefully keep everything that was in there originally, including the comments, and you can convert back from ERF to PCAP-NG as well. But of course some of that information gets dropped because it doesn't translate.
Could you write a replacement, well not a replacement of a dump cap, but if you invoke a capture in Wireshark in ERF format, because you're not just running your own sort of dump cap version which did everything that you said and generated the ERF packets?
That's a good point. So the question is, could you use extcap to produce capture files that have more metadata in it than dumpcap does? Yeah. So I understand that the way dumpcap works today is that it basically provides an interface description block for each of the capture interfaces to Wireshark, which Wireshark then uses. So we could extend that. So if there's more metadata that people want, we can improve dumpcap to include that. Or as you said, if you're capturing live from a DAG interface, for example, with the native APIs, we could collect all that information and pass it through. Until I think Wireshark Europe, a problem was that the XCAP interface only worked with PCAP. It actually only supported PCAP data coming back. And one of the things that's been fixed since then is it should now support different formats. So you should be able to pass ERF records into XCAP and that should work.
Is it also true that, you know the bit where you show things like optical power and link state and things? That would only work if you say on a tap that can see the optical power and link state, wouldn't it? If you were behind a network packet broker, you probably wouldn't see that stuff, would you?
Right, that's a good point. So the comment there was there's no point recording the optical power. The optical power is useful if you're attached to a tap, to an optical tap, but if you're behind a packet broker, then it's not going to tell you anything because it's only going to document the link from the capture device to the packet broker. So one of the things that we kind of thought about there was to have information from the packet broker stored as well. So for packet broker devices which have APIs that let you query information from them about, what are the links that are connected and all that sort of stuff, it would be nice to scrape that off and then store that in the capture metadata as well. And that way we could do things like track the packet broker port and then copy that through as well. That's TBD. I don't think that there are industry standards for packet broker interfaces. I think a number of them have RESTful APIs and things. We need to work on that.
How many bytes of metadata are you adding in the ERF format?
So the question is how much metadata are we adding? I think, so with these periodic provenance records that we're inserting every second, obviously it depends how big the comments are that you put in if you're editing strings by hand, but a 4 interface, a capture system with a 1 capture card and 4 wire interfaces will fit into about 2 kilobytes. So we're adding something like 2 kilobytes per second per capture device, if you like, to the trace file. So it's reasonably lightweight, I would say. Okay, thanks. If you do have any more questions, as I said, we'll be at the vendor evening, and I'll be around for the rest of the conference as well. Happy to answer any questions. Thanks for coming along.